All right, so we're going to pick up with, or where we left off with proportions, and now we're going to talk, ratios, and now we're going to talk about what a proportion is. A proportion is a statement that two ratios, two comparison statements are equal. And we usually write a proportion in fraction form, comparing A is to B, C is to D is how you would read this right here. So to solve a proportion, you can use your proportional reasoning, just like we talked about earlier, like this times 3 is that, that times 3 is that. Or you can also set equal the cross products, which is a fancy way of saying you cross multiply. So every proportion has two cross products. You have the means and the extremes. And these are called the extremes. Don't ask me where they got those names, but A times D is the product of the extremes, and B times C is the product of the means. And so sometimes you'll hear another way of saying you cross multiply is you say the product of the means equals the product of the extremes. So, and this extremes was just supposed to go there, and means supposed to go there. All right, so you guys have done this before. So when you cross multiply, 6 times 3 is 18x. And we have 4 times 27 is 108. And we divide both sides by 18. And x equals 6. Right? So same thing in part B. The only thing that's a little bit more exciting is you get to set up the problem yourself. So the ratio of the width to the height, so just like we talked about before, width comes first, so it's our numerator, height comes second, so it's our denominator. So width to height of a window is 2 to 7. So 2 goes on top, 7 goes on bottom. The width of, I can't read what that says, of the window is 3 feet, right? And solve the proportion to find the height. Maybe that was 6. Okay, I think that just says the width of the window is 3 feet. So how we're going to do this is, since we're doing width to height, we got to make sure that our width is on top in both and our height is on bottom in both. And so your width over here is 3. It says write and solve a proportion to find the height. So our height we don't know, so we're going to call that x. So when we cross multiply, 3 times 7 is 21. 2 times x is 2x. Divide both sides by 2. And x equals 10.5. And that would be your height. And we know it's feet because those were the units we were using, 10 feet. All right, so you try. So pause the video here, write your proportion, and solve it. Ready? You try. Okay, so again, male to female, that's our clue that we need to do males in the numerator, females in the denominator. And since over here it says males are 18, we make sure that we put that on top. And we cross multiply. 18 times 4 gives us the 72. Divide both sides by 3, because 3 times x was 3x. And x equals 24 females. So let's take a look at another one. The ratio of male to female students in the Harry Potter Club is 2 to 3, male to female. This one's a little bit different. Because before we did 2 to 3, male to female, but there are 60 students total is a little bit different, right? So this time, instead of comparing male to female, we're comparing two parts and a whole. So when we think about two parts and a whole, it's back to the same strategy we used with the triangles and the rectangles before. We know that sum 2 times something plus 3 times something will equal 60 total. Again, we're thinking of it as the ratio was 2 to 3, and together these numbers used to equal 60 before they were reduced. Used to be times some number. There was something over here that really added up to 60. So anyway, you can solve it algebraically by saying 5x equals 60, dividing both sides by 5, and x equals 12. But that doesn't actually give you your answer. Your answer is 2 times 12. When you plug it back in, is 24 males, and 3 times 12, when you plug it back in, there were 36 females. Okay, so the last thing we're going to look at here is just a comparison real quick of what does it mean to be a ratio versus what does it mean to be a proportion. So keep in mind, a ratio, friends, is just one fraction. But a proportion is two fractions. It's two equivalent fractions, actually. In a ratio, it's important that your numerator and denominator, if you're going to compare those two things, then it would only make sense that they have the same units, right? Remember, cup to gallon, that's great, but that doesn't really compare how big one is compared to the other until we convert it all to ounces. But keep in mind, in a proportion, we had different units, right? We had females and males. Did we have anything else? Do we have like feet and inches or anything? I don't know that we did. But they can have different units in the numerator and denominator on a proportion. So with a ratio, we had to use conversion factors in order to get it all to one unit. In a proportion, we cross multiply in order to solve for the missing part. And then here's some example of what each would look like. So the first one, you would just, there's 2 feet, so I'm going to convert that to inches. So there's 12 inches in a foot. And so, and remember, in a foot, remember when you convert, you have to put your units catty corner from each other so that they cancel out, like so, because one's in the numerator, one's in the denominator. So you end up with 1 to 24 would be your ratio. Over here, we would cross multiply. 3 times 12 is 36. X times 6 is 6x. And so x would equal 6. Okay, you have some bookwork down here. This bookwork is not going to be due until after test day. So that's like next Wednesday, I believe. And then I'm also going to have you look at the key to the notes for the similar polygons. It's a little more straightforward lesson, so I don't think you necessarily need me to video record that whole lesson. The key is on the haiku, and you can just look at that lesson and the key, and I think you'll get the examples just fine. So I will see you guys on Tuesday. I will be there Tuesday morning at 7:30 if you need any help, as well as on Monday. Okay, bye guys.
Okay, here we are on GeoGebra, and here's that same picture. And the instructions say move point C to change the size of angle A. And so when I move point C, lots of things are changing. Every number on here except for the 11.36. That's the only number that's not changing. All the other numbers are changing. So we're definitely changing that angle. We're definitely changing this opposite side length and the hypotenuse side length, but the adjacent side length is staying the same. Okay, then the second thing to do, it says move point A to change the size. And so now, the numbers are changing on the sides of this triangle, but they're not changing anywhere else. So notice that we're not actually changing the shape of this triangle when I drag point A. I'm only changing the size. Is it big or is it small? But it's the same shape. However, before when we were changing C, we were altering the shape, right? We were making it we were making it a taller triangle or a shorter triangle. Okay, so let's think about what's going on here. So because we were altering this angle, that changed the shape, but when we altered this side length, but not the angle degrees, it doesn't alter the shape. In other words, we've got two angles here that stay congruent no matter how big or how small I make this triangle. In other words, every single triangle, this big one, and this one, and this one, and this one, and this one, they are all similar. They are all proportional by angle, angle, squiggle. So notice how that tangent ratio right here, that 0.33, doesn't change at all, because the whole time I'm doing this 1.57 number over the 4.71 number, but whatever it is, it reduces to that same 0.33, just like 3.99 divided by 11.94 also reduces to 0.33. So what happened is there's infinitely many triangles between here and here. Is once upon a time, this guy named Hipparchus, he recorded all of those different triangle sizes in what's called a trigonometric table. So here, and I cut it off for the sake of having enough space in our notes, but he recorded all the different degrees you could have for angle A, 1, 2, 3, 4, 5, up through 22 on that side. Again, I cut some of these off for the sake of space. And then he recorded when you had, so what was our angle a minute ago? It was 18.48. So let's go back here. And when it was 18.48, the tangent ratio was about 0.33. Let's go look at 18.48. 0.32, that's about 0.33. So what he did is he said for every triangle out there that has 18 degrees and 90 degrees, the ratio of the opposite to adjacent sides will be about 0.3249 or about 0.33. So kind of cool. And so what we're going to do next is we're going to use this table to solve. So this is pretty cool because before, if I had sides of triangles, I could solve for other sides of triangles, and if I had angles, I could solve for other angles. But now there's a connection between the two, between angles and sides. So it says the Greek astronomer Hipparchus was the first to compose a table of trigonometric values. That is, he wrote down all the possible degrees of angle A in a right triangle and then calculated and recorded the opposite to adjacent ratios, each side measure of A. A few years later, Ptolemy improved upon Hipparchus's tables and wrote the book The Almagest, which is considered to be the greatest astronomical work of antiquity. So it was a big deal. I mean, this is like the difference between being able to navigate by the stars out in the ocean and just being lost in the ocean. So it's a big deal. So here's what we've got here, friends. We've got tangent of the angle, we'll call it tangent A, is equal to opposite over adjacent. We know that much. That's the definition of tangent. So what this means is there's a relationship between 22 degrees. Every single triangle that has 22 degrees is similar to every other triangle that has 22 degrees. And so they all have the same opposite to adjacent ratio. So 22 degrees, if I look that up in the table, is 0.4040 for the opposite to adjacent ratio. Aha, so that must be equal to this triangle with 22 degrees and her opposite to adjacent ratio. So her opposite side is x and her adjacent side is 3. So since all triangles with 22 degrees have the same number for their ratio, this one must have that same number. And now I just solve. Now, you can multiply both sides by 3, or you can cross multiply. I'm going to cross multiply just because it works every single time. So x times 1 is x. 3 times 0.4040 gives us 1.212, and then I think we were supposed to give our answer to the nearest tenth, so 1.2 is our answer. Okay, so I'm going to let you pause the video and try to set up this next one. So take a second, label your sides, which one's opposite, which one's adjacent, set up your problem, and then we'll come back and look at it together. Okay, so hopefully you said 12 was across from, it's the opposite side. X is next to, it's the adjacent side. And so tangent of 55 equals opposite 12 over adjacent x. So then you go to your table, tangent of 55, whoops, is 1.4281. Again, we're going to cross multiply to solve this situation for x.